Okay, so in this video we're going to take a look at the binomial series, right? So we're going to focus on finding the Maclaurin series, right? So centered at 0 of the binomial series, and this is what we're going to call the binomial series. All right, where really R is going to be any real number. Right, but we're going to focus on the non-negative integers, right? So, for example, we'll look at values like, first of all, like this. Right, so we get the idea, right? F of x equals to 1 plus x cubed, 1 plus x to the 4th, right? The first one, that value is just 1. This one is 1 plus x. And this one, we have to forward this out, right? So this becomes 1 plus 2x plus x squared, right? It's not 1 plus x squared, right? Please do not do that, all right? And the same thing for cubed, right? It's 1 plus x, 1 plus x times 1 plus x, right? And you would FOIL these out, right? This one, and then kind of distribute again when you have your when you multiply these first two. Now, that is a lot of multiplication, but really here's a neat trick that we can do, right? So what I'm going to draw here is what's called Pascal's triangle. So the way it starts is, so we'll start with the 1, and then each row in Pascal's triangle will add another number to it, right? Always start with 1, always end with 1, right? So the next one here, we're going to start with 1, but now we need 3 elements. The way I'm going to come up with the middle one is I look at the numbers that are right above it, to the left, to the right, and I add them. So to the left and to the right, we get 1 plus 1, which is 2, and then it ends with 1. All right, so always bookend it with 1. So the next few rows will look like this: 1, right? The next one, look above, to the left, to the right, 3. One more time, left to the right, 3, 1. Right, and then here, 1, left to the right, 4, 6, 4, 1, etc. Right? So what we have here is these coefficients. If you see here, the first one, 1, they match up with the coefficients of my binomial expansion, right? 1, 1, 1, 2, 1, right? And we can kind of guess from here, this will be 1 plus 3x plus 3x squared plus x cubed. Okay, and we see the nice symmetry here. So x, excuse me, this to the 4th should be on the outside. So we could see the next level, 1 plus 4x plus 6x squared plus 4x cubed plus x to the 4th. All right, so we can do that binomial expansion rather quickly, right? So what these numbers represent, right, these coefficients, they have something that's called the choose number, right? If you ever take a combinatorics course, it becomes very important. So it's written like this, right? R choose n, right? And what that is, here's the algebraic. So maybe sometimes you don't have the time to build the whole triangle. The actual algebraic calculations look like this: r factorial, n factorial, r minus n factorial. Right, so that's how you would calculate something like this, right? Where r is the row, and n, you can think of it as the element in the row, right? So here, and again, with these kind of combinatorial operations, right? And if you ever taken a computer programming class, right, this should be probably common or something that you've seen before, is we start counting at 0, right? So the 0 row is here, the first row, the second row, the third row, right? And then the bottom part, n, is the element in that row, right? So all these ones are always the 0th element, and these last ones here, it's still 0, but this one is the first one. the second one, right? The third one, etc., right? So something like row 3, second element, right? So you would go to, actually, let me give myself some space here. So something like the third row, second element. All right, so here 0, 1, 2, 3. The second element 0, 1, 2. Right? So that would be 3. Right now, in terms of this algebraic calculation, right? 3, choose 2. Right? 3 factorial, 2 factorial, 3 minus 2 factorial. Right, and this becomes, right, 3 times 2 factorial over 2 factorial, 1 factorial. So the 2 factorials, 1 factorial is just 1, and we're left with 3. Okay, so that's how those numbers work here, right? And in general, right, what that allows us to do now is that we can now have a generalized form here of our binomial expansion here, right, where this would go r to the 0, right, times 1, right, plus r1, right, x plus r2, x squared, etc., till we get to the third one, r, which itself is 1, right? If you look at the operation, right, when they're equal, you just get the 1, which makes sense. That's the bookend of my triangle, right? X to the r. Okay, and in our sigma notation, right, n is equal to 0 to r, or r choose n, x to the n. All right. Okay, and so in general, if let's say we had 1 plus x to the 5th, that equals to the sum n equals 0, 5, choose n, x to the n. All right, and that expansion is 5 choose 0 times 1 plus 5 choose 1 x plus 5 choose 2 x squared. Let me continue it here. 5 choose 3 x cubed plus 5 choose 4 x to the 4th, and then 5 choose 5 x to the 5th. Okay. All right, and then if we were to, again, can multiply those out, right? I won't, here we can really just to make things quicker here, adding to our next triangle here. That'd be 1, 5, 10, 10, 5, 1. Okay. All right, so those would be the coefficients, right? 1, 5, 10, 10, 5, 1. 1, 5, 10, 10, 5, 1. Okay, all right, and we have our expansion here. Okay, now here, if we notice, what if, so this works fine when we have non-negative integers, right? But let's expand our definition here where r can be any real number, right? Not necessarily a non-negative integer. So we would start again with the Maclaurin, right? Centered at 0, right? Where we have f of x to be 1 plus x to the r, right? And what I mean by non-negative integers, I'd like for r can equal to, let's say, -1, right? Or r equals to 1/2, all right? Really just any real number, right? And let's see, and then as we discussed in the beginning of the semester, right, we can differentiate, we can use the power rule for any irrational number too, right? So for whatever reason, r can be pi, right? In case we're interested in that function for some reason. All right, so building a Maclaurin, right, we know we need a derivative, right, or the nth derivative here. So r1 plus x to the r minus 1. Second derivative, r minus 1, 1 plus x to the r minus 2. Okay, and then kind of keep it going here. The third derivative of x is r minus 1, r minus 2, 1 plus x, r minus 3. Right, and we can kind of see the pattern here. The nth derivative would look like r minus 1, r minus 2, right? And then we'd stop short of n minus 1, because that would be the nth. Here, the nth power would be here, right? As we see here, third derivative matches up here, and this value is 1 less than the derivative that we're at, right? So it would stop at r minus n plus 1, right? A couple things, just think of this as this, right? 1 short of n, and the derivative or the exponent here would be 1 plus x to the r minus n. Okay, so that would be the nth derivative here. Right? Now centered at 0, so if I center this at 0, right, f of 0 is 1, f prime of 0 is r, f double prime at 0, right? So when that happens, right, we just get 1 to some exponent, which again, always 1. So really we're just left with the coefficients here. r minus 1, 0, excuse me, triple prime of 0 is r minus 1, r minus 2, right? And in general, the nth derivative at x here, right, this quantity here just goes to 1. So we're left with r minus 1, r minus 2 to the r minus n plus 1. So that means in our Taylor expansion, the Maclaurin series, the nth coefficient, right, our c sub n is f, the nth derivative evaluated at 0 over n factorial, which is r minus 1, r minus 2, r minus n plus 1 all over n factorial. Okay, so now this general form here actually conforms with our previous understanding of what the choose number here is, right? If this was a non-negative integer, right, if we were to take the derivative of, let's say this one, right, if it's 5, right? So in general here, let me, before we keep going here, yeah, okay. So here, this quantity here, right, when I do have a non-negative integer, right? So what I mean by non-negative integer, if we do have values that are 0, 1, 2, 4, right? This formula simplifies or reduces to the choose number, right? It is, in fact, r choose n, right? When r is 0, 1, 2, not 4, just in general, right? Any value of that, right? 50, 500, whatever. All right, then that formula converges to the r choose n, right? But now we just wrote it like this because written like this, it it's to include any real number. I can do this operation here. All right. So what we have is for the binomial expansion, the series, and this would be for any real number r, right? R is the element here. Then I have an infinite series. X choose n, right? Where this r choose n number can be is this formula up here, right? But we allow for r to be any real number. So if it's a half, I can continue using this infinite series, right? The thing when it is a non-negative integer, when it's one of these, is that the series doesn't go to infinity. At some point, that derivative would be 0, right? Think of if the power was 5. If you apply the power rule, eventually you'll get to the power of 0, which is 1, and then anything after that, the derivative would just be 0, right? So even though it says to infinity, right, if the power was 5, right, it would have 5 terms, right, or 6 terms, right, because we start counting at 0. All right, that next derivative would just go to 0. Okay, so just keep that in mind, right? These are allowed for r to be any real number, but if r happens to be a non-negative integer, this is not an infinite series, but it's a finite series. Okay, now the interval of convergence. So we'll take a look, we'll use the ratio test. So if I do that, here we have r times r minus 1, or r minus 2, r minus n plus 1. All right, and then if I go the next one over, right, we just get r minus n plus 1 plus 1. All right, and times x to the n plus 1 all over n plus 1 factorial, and then division I'll just multiply by the reciprocal. Sorry, it gets a little long here. N factorial over r minus 1, r minus 2, all the way to r minus n plus 1, and then times x to the n. All right, I didn't put the factorials in absolute values because those are going to be positive anyway, so I don't need to worry about the absolute value around there. All right, and then we see what happens here is that here, right, this cancels with this here. All right, x to the n plus 1, x to the n, so we're left with 1 factor of x. So we get here the absolute value. We have r minus, this is what's left here. That minus 1 cancels here, right, if I distribute the negative. So we get r minus n times the absolute value of x over, right, n plus 1. Okay, here. All right, yes. Okay, and here if I take the limit as n goes to infinity of a sub n plus 1 over a sub n, and the ratio test, we get limit as n goes to infinity that x does not depend on n. So I can write it out here, and we get r minus n over n plus 1, right? And as n goes to infinity, right, that's what's changing, right? R is fixed, 1 is of course fixed. So we get the absolute value of negative n over n, which is just positive 1, right? Since it's absolute value. So the limit goes to 1. We have an absolute value of x on the outside. So we get this, right? So it converges when the absolute value of x is less than 1. In other words, we have 1 to be my radius of convergence. Okay. All right. So let's look at how do we use this series here. So for this example, I want to find the binomial expansion, find the binomial series for f of x equals to 1 over 1 plus x squared. All right. All right, keep in mind that this is 1 plus x to the negative 2. All right, so my series for f of x is negative 2, choose n. The sum n equals 0 to infinity. Negative 2, choose n, x to the n. All right. And here, writing out a few terms here, we can probably simplify this a little bit. So when n is 0, right, x to the 0 is 1, right? Negative 2, choose 0, that's going to be 1 as well. All right. Whatever that value r is, if the n is 0, that number will always be 0. So we move on when n is 1, right? We get negative 2, right, over 1 factorial, and then plus times x, and then we get negative 2 minus 1, right? We each step of the way, we subtract 1, right? 2 factorial, so we have 2 terms, x squared, and then plus negative 2 minus 1, negative 2 minus 2, all over 3 factorial x cubed, and plus dot, 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 dot. All right, if we simplify this, here we get 1 minus 2x. Here, what we notice here, this becomes, so this will be positive, right? This is negative, so it's plus 2 times 3 over 2 factorial. And then this one, so we have minus, 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 so the whole thing is minus. And we get 2 times 3 times 4, all over 3 factorial, right? X cubed. Right, and we can kind of see the pattern here, right? The next one, it's alternating, right? And we can see here the next one, and have 4 factorial, 2, 3, 4, 5. Okay. All right. And what we do notice here is, well, notice here that here you can always multiply in the 1, right? That doesn't change anything. Like, for example, if I just write 1 times, 1 times, 1 times, right? Now I do that to illustrate that this is 2 factorial, this is 3 factorial, this is 4 factorial, and then, sorry, I forgot the x here, times x to the 4th. Right, so if I simplify further, we get 1 minus 2x, x squared, plus 3x squared minus 4x cubed and then plus 5x to the fourth. Okay. All right, in general, we can write this using the sigma notation. N goes from 0 to infinity. Here, and notice here that we don't go to 0 here, right? This is an infinite series, right, where the coefficient is always 1 more than whatever the power is. And it's also alternating, so it's -1 times -1 to the n power. Right, so when this is 0, right, just kind of mentally you can double check here, right? This value is 1, x to the 0 is 1, and this is -1 to the 0 power, also 1. So multiply through, it's all just 1. When n is 1, now we get 2, right, the 2 here, to the first power, and then 1 here gives me odd, so that gives you that negative, and etc. Right there. So that's how we can apply the binomial expansion here.